Welcome to INSITECT. Today we are talking about the infrastructure, security, and complex cabling behind centralized TV systems in apartment buildings.
We're doing a deep dive into the engineering specs, the actual manual for installing shared satellite reception.
And this is for what's called SMATV, right?
Yeah.
Satellite Master Antenna Television.
Exactly, for multi-dwelling units. And our mission today is to show you that this is really not just about getting TV channels to people.
Right.
It's a master class in, resilient signal distribution, network topology, and just overcoming some really severe architectural constraints in a critical building system.
And for property manager, the first thing you think of is probably aesthetics.
Right.
It gets rid of all that clutter on the building, no more dishes bolted to every balcony.
Sure, that's the obvious part.
But the sources we looked at really point to reliability. A shared dish simplifies maintenance, and it just stops all those service calls you get from tenant dishes that, get knocked out of alignment by a storm.
It's an operational necessity, really. If you have, say, 100 individual dishes, you suddenly have 100 separate points of failure.
All using cheap consumer-grade mounts.
Right. By centralizing, you invest once in one high-quality professional installation, and that standardizes the service, and it just drastically cuts your long-term maintenance costs.
So let's get into the technical core of that. Why is it more reliable? Moving past aesthetics, why does one single professional dish actually outperform dozens of smaller ones?
It's absolutely about the quality of the components, specifically the low-noise block-down converter, the LNB, and the precision of the dish itself. A professional-grade dish isn't just bigger.
No.
Its curvature is manufactured to a much higher tolerance. It can focus that incredibly weak signal from 22,000 miles away much more effectively.
And the LNB, what's its role in all this? What does it actually do?
It has two critical jobs. First, it amplifies that signal, which is unbelievably faint when it hits the dish. And second, and this is crucial, it performs a frequency shift.
It down converts it.
It down converts it. It takes that super high satellite frequency and shifts it down to a lower range that can actually travel over standard coaxial cable without massive signal loss. A Pro LNB does this with more gain and a much lower noise figure than, anything you'd buy at a big box store.
So the signal starts its journey inside the building in a much, much cleaner state.
Precisely. And that high-quality signal is then handed off to the real brain of the operation, the multiswitch. That's where signal prep ends and the distribution network really begins.
And this is where it gets really interesting for me. I remember older systems, these passive splitters, where if I wanted one channel and my neighbor wanted another, we could actually cause a conflict.
Oh, absolutely. A voltage conflict.
Right. So what makes the modern multi-switch the aha moment that solves this?
The modern multi-switch is an active traffic director. It's not passive. It receives all the different signals from the LNB. You have horizontal high and low, vertical high and low. The key is how it listens to the receiver in the apartment.
So there's communication going back up the cable.
Yes. It uses control tones. When your receiver requests a channel, it sends a specific voltage, say 13 volts for vertical polarization, or it might add a 22 kilohertz tone for the high band. The multi-switch detects that command.
And it routes only the specific signal that receiver asked for down that specific cable.
Exactly. It does this simultaneously and independently for potentially hundreds of units. The channel conflict is just completely eliminated.
But wait a second. Doesn't centralizing everything on one piece of hardware create a massive single point of failure? If that multi-switch dies, the entire building goes dark.
That is a very important point about risk management. And you're right, functionally it is a single point of failure.
So why is that about a risk?
Because it's a managed risk. The system design calls for commercial-grade equipment built for continuous use, not consumer hardware. And more importantly, the failure point is contained. It's visible. It's in a telecom closet, not on Mrs. Smith's balcony on the 14th floor.
So the cost to fix it is known and predictable.
It's fixed and manageable. The alternative is this distributed failure model where a manager is constantly chasing intermittent faults across dozens of apartments. That means higher labor costs and, frankly, nonstop tenant frustration. It's a trade-off.
Okay, that makes sense. So let's talk about planning. Before you even pull a cable, the site survey is everything. You have to have a clear line of sight, which sounds simple, but what are the biggest constraints people underestimate?
Well, the precision required is almost absurd. You're trying to hit a target 22,000 miles away that's in a fixed orbit. The manual dictates that you need about 5 degrees of clearance on all sides of your target direction.
5 degrees, that's like threading a needle. It's not just pointing it south.
Exactly. And the problem isn't just another building blocking you. We've seen cases where a new, small tree branch or even a new architectural feature on a neighboring building can cause intermittent signal loss.
And that gets worse in bad weather, right?
Of course, wind or heavy rain makes the obstruction move, and that creates these unpredictable signal shadows.
So let me play devil's advocate. If the line of sight is so fragile, why not just brute force it? Get the biggest dish possible to power through minor issues. Is bigger always better?
It's about being smart, not just big. You match the dish size to the local climate. The source material is very clear on this. In places with heavy rain, like, say, Florida or the Pacific Northwest, you oversize the dish by 1 step.
And that's not for better aim, it's for something else.
Right. It's specifically to build in an extra margin of signal gain to fight what we call rain fade. The moisture in the air literally absorbs the microwave signal. That extra gain keeps the picture stable when a smaller dish would start to pixelate.
And that planning for resilience, that has to extend to the multi-switch too. It's not just about today's tenants.
That is one of the most common and costly mistakes. You have to calculate the total number of receivers you need today, and then you add a non-negotiable 20% buffer for future expansion.
20%.
That 20% buffer is the difference between a 1-hour job in 5 years and a full system rip and replace because you ran out of ports. It's the best insurance you can buy.
This brings us to path loss, making sure the person in the penthouse gets the same great signal as the person on the ground floor. How critical is that pre-installation math?
It underpins the entire design. We have to account for every little bit of loss. That tiny F connector that joins 2 cables, that's about 0.3 decibels of loss right there.
Which sounds like nothing.
It sounds like nothing, but in a big building with dozens and dozens of connections, it adds up incredibly fast. Then you have your splitters, which can add another 3.5 to 7 decibels of loss each.
So what's the magic number? The threshold you can't cross.
If your total calculated loss along any single cable path exceeds 15 dB, you are guaranteeing problems at the far end. If the math shows you're going to hit that, you must design an align amplifier to boost the signal back up. Ignore that, and the bottom floors will be calling you every single day.
So the signal is clean, it's amplified, now it has to get through the building. What's the best way to lay out the cabling to avoid all the interference from the building's own systems?
Well, the main arteries are the vertical risers. They run up through dedicated shafts, and they have to be in their own conduit. A key detail here is to leave what we call service loops at each floor.
Those coils of extra cable you sometimes see, they look messy.
They look messy, but they're absolutely vital. They give you slack for future repairs or modifications without having to pull a brand new cable from the roof to the second floor.
And once you get to a floor, you have to split the signal to the apartments. Star versus daisy chain. This seems like a pure risk decision.
It is, and the star topology is always preferred for a professional MDU installation. It means a dedicated cable runs from a floor splitter directly to each unit.
So if one cable gets damaged,
only that one apartment loses service. The source explicitly recommends star for any building with more than 6 units per floor because of that isolation.
and a daisy chain saves cable, but it's a huge risk.
Oh, a huge risk. You're compounding signal loss at every stop, and worse, you create a cascading failure point. A short circuit in one apartment can take out every unit downstream from it.
Now, you're running these sensitive cables right next to elevator motors, HVAC, all kinds of electrical noise. How does the cable itself fight that off?
This is where your choice of material is your primary defense. The spec is RG6 quad shield coaxial cable.
Quad shield.
Standard coax might have 1 or 2 layers of shielding. Quad shield has 2 layers of foil and 2 layers of braid. It provides superior rejection of all that electromagnetic and radio frequency interference.
And if an installer cuts corners, uses cheaper cable, what does the tenant actually experience?
They might get intermittent buzzing in their audio, or you'll see visible wavy lines on the screen, especially when a big motor like an elevator kicks on. You have to keep the cable runs as far away from those high-power feeders as possible.
Okay, so we have the satellite signal covered. But people still need their local broadcast channels. How do you get both of those onto the same single cable?
You use a component called a diplexer. It's an integration layer. Satellite signals live up in the high frequency band, from 950 to 2150 megahertz.
Right.
Your local over-the-air channels are way down in the low band, 47 to 862 megahertz. The diplexer intelligently combines these two different frequency ranges onto one coax cable.
And then it gets split back out at the wall plate in the apartment.
Exactly. A reverse diplexer separates them again. The most critical spec for that diplexer is isolation. It has to provide at least 25 D-dollars of isolation between the two bands. Any less than that, and the strong local signals can bleed into the satellite band and just corrupt the signal.
Let's move to safety. You have all this metal and electronics on the roof, the highest point around. Lightning is a serious risk.
It's an absolute imperative. You have to bond the dish mast directly to the building's main grounding system, and the spec is a thick 10-gauge copper wire.
And what about the cables themselves?
Where the coax cables enter the building, you install a coax grounding block. This connects the shield of every single cable to that same ground. It creates a safe path to Earth for any static buildup or, a lightning surge, so it doesn't fry all your expensive internal electronics.
And the physical mounting has to be engineered too, right? Especially on a high-rise.
Oh, absolutely. You're often using non-penetrating mounts, which are basically big sleds weighed down with concrete blocks to avoid voiding the roof's warranty. And for any tall building, that installation needs an engineer's stamp to make sure it can withstand hurricane-force winds.
Okay, let's troubleshoot. Say the system is running. We know how to fix low signal strength. But what about the really tricky issue? The meter says the signal is strong, but the tenant sees constant pixelation or freezing.
That is the classic sign of interference, or more likely, multipath reflection.
Multipath, so an echo of the signal.
It's exactly like an echo. Imagine the dish is installed perfectly, but then the building next door puts up a big metal awning. Now your dish is seeing the main signal from the satellite and a slightly delayed reflected version bouncing off that new surface.
And the receiver just gets confused trying to process both at once.
Precisely. It causes digital jitter and pixelation, even with high signal power. You can also get it from internal RF noise, but multipath is a common one. And you also have to check the connectors. A poorly compressed connector lets moisture in, and that causes corrosion and all sorts of intermittent problems.
So finally, let's talk about keeping the system alive for the long haul. What parts have to be replaced proactively before they fail?
This is all about proactive life cycle management. The two components that are under the most stress are the LNB on the roof and the multiswitch's power supply.
And what are their typical lifespans?
The LNB, which is exposed to extreme weather, will usually start to degrade after 5 to 7 years. Its internal noise figure creeps up, and your performance margin goes down. The multiswitch itself is pretty robust, but its power supply is the weak link. You should budget to replace those every 3 to 5 years. The electrolytic capacitors inside them just break down from the constant heat.
And if you wait for that 5-year-old power supply to fail, it'll be on a Saturday night and the whole building goes dark.
Without fail. The small cost of a proactive replacement is nothing compared to the massive cost of an emergency call-out in a building full of angry tenants.
So when we boil this all down, our deep dive really shows that an SMATV installation isn't just a simple cabling job. It's a microcosm of serious network engineering.
It really is.
Long-term resilience is all determined by this meticulous attention to physical constraints, like that 5-degree line of sight, doing the math to understand that even a 0.3 dB loss per connector matters, and having a strict replacement schedule for parts like LNBs.
And I think the most provocative thought to leave you with is that the real value of this infrastructure is its adaptability. Because it was designed with that 20% expansion buffer and that resilient star topology, the investment is future-proof.
Meaning you can add new services later on.
Exactly. You can often add a whole new satellite position or integrate new technologies with just minimal changes. It's a powerful lesson in designing physical infrastructure to expect and to manage technological evolution.
Thanks for listening. We will continue to talk about security and technology. See you in the next episode.